So in this video, we're going to be talking about thermal expansion in liquids. We will introduce thermal expansion in liquids, talk about the types, and solve relevant examples to back up all our explanations. Now, as you all know, liquids do not have a standard structure or area of their own, but they assume the volume of any container which they are stored. As a result, in the case of liquids, we are only concerned with the change in volume whenever they are subjected to heat. So this brings us to the idea of thermal expansivity in liquids, or thermal expansion in liquids. Thermal expansion of a liquid simply refers to the increase in dimensions when heated. So whenever a liquid is being heated, there is always bound to be an increase in dimension. Now let's show a diagram to illustrate this definition. Now this diagram shows an image of three containers which individually have a thermometer in them. This thermometer is used to measure the different amount of temperatures that are in each of these containers. Now observe the dimension of the first container. The dimension of the first container is quite smaller compared to the second container and the last container. Now there's a reason for this. Also, one other thing I want you to observe is the agitation of liquid molecules in this container. Now each of these containers are containing liquids. Now these blue spheres here represent the molecules of liquids in these containers. Now observe the movement of the molecules of liquid in the first container is not as rapid as compared to the second, and the second is not as vigorous as compared to the third. So in the first container, the temperature level is quite smaller. As a result, the volume is the normal volume of the container, right? And since the temperature level is small, it means that the kinetic energy of the molecules of the liquid are quite smaller, which actually yields a minimal increase in the volume of the container. But when the temperature increases, as can be seen in the second image, there is a rapid movement of the molecules of the liquid, because at this point, due to the increase in temperature, the molecules of liquid increases in kinetic energy. And since they increase in kinetic energy, the container also increases, being subjected to heat. The container also increases in volume. So you observe the volume of the first container and the second one, they are quite different. The second container is quite larger in volume compared to the first container. This is because the increase in temperature results into an increase in the volume of the container, also resulted into an increase in the volume of the liquid itself, because the liquid molecules now gain higher kinetic energy and they can move rapidly due to what? Increase in temperature. Now the same thing happens in the third container. In the third container, the temperature is even higher than in the second container. That led to a vigorous movement of the molecules of liquid because of high kinetic energy that have been gained due to the increase in temperature. The volume of this container is also seen larger than the second container, because when this container is being subjected to temperature or to heat, it is increased as much as the kinetic energy of the liquid molecules also increases, leading to a vigorous movement of the liquid molecules. So now one thing you have to pay attention here is this: with the higher the temperature, the lower the liquid level in the container. So when the temperature is higher, the volume of the container expands. That will lead to a decrease in the level or height of liquid inside the container. So when liquid in the container is being subjected to heat, there's always going to be an increase in the volume with respect to the original volume of the container. So the first image tells us the original volume of this container. Now the final image tells us the new volume. So there's always an increase in the volume of the container with respect to the original volume, with respect to also the change in temperature. Because what caused this volume, the volume of the third image, to increase rapidly is the increase in temperature. So that brings us to the mathematical definition of thermal expansion in liquids. And that can simply be defined as the increase in the volume of the liquid with respect to the original volume of the liquid with respect to the change in temperature. So mathematically, the thermal expansion in liquid, or the coefficient of thermal expansivity, beta, is going to be equal to the change in volume with respect to the original volume with respect to the change in temperature. So this is simply equal to change in V for change in volume all over original volume is VO times change in temperature, where change in V simply means change in temperature, and change in V means the final volume V1 minus the original volume VO. And change in temperature, also change in T, simply means final temperature T1 minus the initial temperature T0. And VO there simply means the original volume of that given container. Now let's apply this formula to solve a few examples before we go on. Now let's consider this question to explain what we've learned so far. Question says a 250 ml flask is filled with alcohol at 25 degrees Celsius. When heated to 75 degrees Celsius, the alcohol overflows. If the coefficient of volume expansion of alcohol is 1.1 by 10 to the power of -3 per degree rise per degree Celsius, calculate the volume of alcohol that overflowed. So let's pick out our parameters. So we're given from the question a 250 ml flask is filled with alcohol. So which means the initial volume is 250 ml. So original volume of alcohol, that's VO, is equal to 250 ml. Now it's filled with alcohol at 25 degrees Celsius. So original temperature that is T0 or T0 is actually 25 degrees Celsius. Now the question says when heated to 75 degrees Celsius, so we have our final temperature. We call that T1 equals 75 degrees Celsius. Okay, they said the alcohol overflows, so which means we have a final volume which is unknown. So final volume, which is V1, is unknown. Now we are given that the coefficient of volume expansion of alcohol is 1.1, and that is beta, coefficient of expansion that is beta, was given as 1.1 by 10 to the power of -3 per degree Celsius. Okay, sorry about that. Okay, per degree Celsius. Alright, so we have to find the final volume that overflowed. So you recall your formula. Okay, recall the coefficient of thermal expansion beta is equal to change in volume with respect to the original volume times change in temperature. Okay, where change in temperature itself is actually T1, final temperature, minus original temperature. So this is equal to, from the question, our final temperature is 75 degrees Celsius. So one thing you need to know is, do not hurry to want to convert temperature to Kelvin by adding 273 Kelvin, right? Do not hurry to do it, because if you do it, when you subtract here, they will still cancel out. So we have 75 degrees Celsius minus 25 degrees Celsius. So like I said, do not convert, because when you subtract here, you will still have the same result upon conversion. So converting would really take your time. So this simply implies that change in temperature is now going to be equal to, we have 75 minus 25. That simply gives us 50 degrees Celsius. So this becomes our change in temperature. Now we know the original volume. Let's make change in volume subject of the formula from this equation. So from the general equation, change in volume is now going to be equal to simply cross multiply the coefficient of thermal expansion in liquid, multiply the whole of this equation under here. So we have beta multiplies by V naught multiplied by change in temperature. So this is equal to the coefficient of thermal expansion from the equation was given as 1.1 by 10 to the power of -3, multiply now by the change in the original volume itself. From the question, original volume was given as 250 mil V naught. So multiply by 250 mil multiply by change in temperature, which is 50 degrees Celsius. Okay, so let's do all of this and see what we are going to obtain. So 50 multiplies by 250 mil multiplied by 1.1 exponential minus 3, and that simply gives us 13.75. So we have 13.75. So this becomes the change in volume. So okay, so this simply implies change in volume is 13.75. So this is the change in volume, but you recall that change in volume itself is actually what? V1 final volume minus the initial volume V naught. So this simply implies that the final volume, which we are asked to find, is now going to be equal to, transferring V naught to the other side of the equation, we are going to have change in volume plus V naught. This gives us the final volume. So this simply implies that the final volume of alcohol V1 is equal to, change in volume is 13.75 plus the original volume from the question is 250 mil. So we have 250 mil. So this simply implies that the final volume is going to be equal to 250 plus 13.75. That simply gives us 263.75 mil. So this becomes the final volume after being subjected to a temperature of 75 degrees Celsius. So you see what happens there? The volume actually increases because the temperature increased, which is what I was explaining earlier. Alright, let's pick one more example for this case before we move on to the next. Now let's consider this question. It says a liquid has an initial volume of 1.5 liters at 30 degrees Celsius. When heated to 80 degrees Celsius, the volume increased to 1.515 liters. Determine the coefficient of volume expansion of the liquid. So let's pick out our parameters. A liquid has an initial volume, so initial volume simply means the original volume. So which means original volume which is V naught is 1.5 liters. Okay, at 30 degrees Celsius. So original temperature, which is T naught, is 30 degrees Celsius. Now when heated to 80 degrees Celsius, so final temperature, which is T1, equals 80 degrees Celsius. The volume increases to 1.515 liters. So final volume, which is V1, is 1.515 liters. We are asked to find the coefficient of thermal expansion. coefficient of expansion, which is beta, and it is unknown. So you recall that beta is actually change in volume with respect to the original volume multiplied by change in temperature. And change in volume is actually V1 minus V0, which is final volume minus the original volume, with respect to the original volume multiplied by final temperature T1 minus original temperature T0. So this is equal to, our final volume is 1.515 minus original volume is 1.5 liters, all over original volume is 1.5 liters, multiply change in temperature, which is final temperature 80 degrees minus initial temperature 30. So once again, do not convert your temperature to Kelvin because they will still cancel out. So this is going to be equal to 1.515 minus 1.5. That simply gives us 0.015 all over 1.5 multiplied by 80 minus 30. That gives us 50. So this simply implies that the coefficient of thermal expansion becomes 0.015 all over. So let's obtain 1.5 multiplied by 50. That gives us 75. So this simply implies that the coefficient of thermal expansivity becomes, let's do 0.015 divided by 75. So we simply have 2 by 10 to the power of negative 4. So that simply gives us 2.0 by 10 to the power of negative 4 per degree Celsius. Okay, per degree Celsius. So that becomes the answer to that given question. So just like we said earlier, since liquid have no predetermined shape of their own, they assume the shape of the container to which they are stored. And as such, when this container is being heated, the liquid expands in volume as well as the container also expands in volume. So this brings us to two types of thermal expansion in liquids. The first is called the real or absolute thermal expansion, and the second is called the apparent thermal expansion. So let's discuss them in details. The real or absolute thermal expansion refers to the percentage change in volume with respect to the original volume per degree rise in temperature. So it is basically the same formula as the definition of thermal expansion, but in this case, the real or thermal expansion is expressed as a percentage. So mathematically, the thermal expansion or the absolute thermal expansion, the coefficient of absolute thermal expansion, so beta absolute, is represented as change in volume with respect to the original volume multiplied by change in temperature. Then you multiply the whole of this by what? 100%. So the absolute or real thermal expansion is a percentage of the absolute thermal expansivity. It's a percentage of the thermal expansivity of a liquid. So all you need to do is, whenever a question is given and you obtain the value of the thermal expansion, you can easily multiply that value by 100 and express it as a percentage. For instance, in the previous examples which we just solved, we obtained 2 by 10 to the power of negative 4 as the value of the coefficient of thermal expansion. So which means in terms of real or absolute thermal expansion, it means for that given value, the absolute thermal expansion will become beta absolute simply becomes what? 2.0 by 10 to the power of negative 4. Now you multiply this by what? 100% and express it as a percentage. So this implies that the absolute thermal expansion for that given question is going to now be equal to that becomes simply 0.02%. So this becomes the absolute or real thermal expansion of that given question. Now, since it is difficult to measure directly the real expansivity or the absolute expansivity of any liquid in a container, that simply brings us to the idea of apparent expansivity. The apparent expansivity in a liquid refers to the observed expansion when a liquid is heated in a container. So whenever a liquid is heated in a container, like we said, the liquid inside the container experiences an expansion, and the container itself also experiences an expansion. Now, the expansion of the liquid is called the real or absolute expansion, whereas the expansion of the container is called a linear expansion. The difference between the real expansion and the linear expansion gives rise to what is called the apparent expansivity. So mathematically, apparent expansivity beta apparent is simply equal to the difference in real expansivity or absolute expansivity, so beta absolute minus the container expansivity. And I said that the container expansivity is actually what? A linear expansion. So we call that alpha container, okay, which is the alpha container. That's the linear expansivity of the container, right? But you recall that I've done a video on linear area and volume expansion in solids. Since the container is always going to be a solid, and you recall that volume expansion is 3 times the linear expansivity of that given container or that given solid. Therefore, this equation can be rewritten as the apparent expansivity, beta apparent, is now going to be equal to the absolute expansion, beta absolute, or the real expansivity, minus 3 times the linear expansivity of the container. So this is the equation that governs what? The apparent expansivity. So like I said earlier, to measure the real expansivity of the liquid is quite difficult as a result of heat. So when heat is being subjected to a liquid, the container itself expands in volume, as well as the liquid inside the container also expands. So in order to measure the real expansivity, that becomes difficult. But there is going to be an observed difference in the volume of the container or in the expansion of the container, as well as in the expansion of the fluid. This difference is called the apparent expansivity. So whenever a question is given to you, if you're able to know the linear expansivity of the given solid and the absolute or real expansivity of the liquid, then we can be able to find what? The apparent expansivity. Let's pick a question now to explain this term. Now this question says a glass container with a volume of 500 ml is filled with a liquid at 20 degrees Celsius. The liquid and the container are heated to 70 degrees Celsius. The coefficient of volume expansion of the liquid is 5 times 10 to the power of -4 per degree Celsius, and the coefficient of linear expansion of the glass is 1 by 10 to the power of -5 per degree Celsius. Calculate the apparent expansivity of the liquid. Okay, so let's pick out our parameters. We are given the initial and final temperature. So original temperature was given, which is T0, and that is simply 20 degrees Celsius. we are given the final temperature, which is T1, that is 70 degrees Celsius. Now we are given the thermal expansion of liquid, which is the absolute expansion. Now please mind you, so we are given the thermal expansion of liquid, thermal expansion, which is beta, and that is given in the question as 5 by 10 to the power of -4. -4 per degree Celsius. We are also given the linear expansion of the container. Linear expansion, which is alpha, of the container was given as 1 by 10 to the power of -5 per degree Celsius. So we are asked to find the apparent expansivity. Apparent expansion, okay, which is unknown. So you recall the equation for apparent expansivity. Recall, apparent expansivity is actually the real expansivity or the absolute expansivity minus 3 times the linear expansivity of the container. So the real expansivity is simply the thermal expansion of the liquid given here, 5 by 10 to the power of -4. And mind you, in this case, you don't need to convert to percentage because you're simply subtracting. So you can simply leave it like that. That is simply the thermal expansion. So that means this is going to be equal to the thermal expansion is the real expansivity, which is 5 by 10 to the power of -4 minus 3 times the linear expansivity of the container, and the linear expansivity of the container is 1 by 10 to the power of -5. So if you do this, you're going to have your absolute expansivity, your apparent expansivity. Okay, you have your apparent expansivity to now be equal to, this is 5 by 10 to the power of -4 minus, this is 3 by 10 to the power of -5. So let's punch this together and see what we are going to obtain. That simply gives us 4.7 by 10 to the power of -4 per degree Celsius. So this becomes the apparent expansivity of that given liquid. Alright guys, so the video is becoming too long. I'll pause the video here, and in the next video we are going to be looking at more examples on the thermal expansion in liquid. I'm sure you want to be a part of that video, so do well to tap the subscribe button right now and turn on your notification bell so you don't miss out on that video when it drops. In the meantime, do well to like this video, comment nicely, share to your friends, and if you're new to the channel, do well to hit the subscribe button. I will see you in the next video. Thanks.